A very good afternoon to all of you. In this lecture today, we will continue talking about the averaging filters or the low pass filter. We will see some nonlinear filters very briefly, and then we are going to look at the mechanics of sharpening filter. That is a brief introduction to it. So these are the three things on our plate today. So we are going to discuss them right now. Use of Laplacian is a part of it. So we were already doing fundamentals of image spatial filtering. So linear filters, as we had seen, we divided them into three categories. Low pass, where it attenuates the high frequency components, which actually leads to image blurring. So normally, remember, we are not doing a frequency domain filtering, but the terminology is taken from the frequency domain filters. Therefore, since the terminology is taken from the frequency domain filters, we use that terminology over here. It should not be misled that we are using any frequency component. Normally, when you use image blurring, it leads to the blurring of sharp edges and repetitive parameters, which is equivalent to a low pass filter. So we call it a high pass filter. The effect of a high pass filter is obtained by suppressing the large objects from the image or slow varying frequencies. It actually leads to the sharpening of edges and other details. The third is the band pass filter. We typically won't discuss that in this chapter. Next chapter, that will be a subject matter. And then we have seen one of the simplest smoothening or averaging filter I had presented. It was presented on the left side. It's a 3 by 3. Remember, the smallest one could be 1 by 1, but that is an intensity transformation that comes under different category of topics. So we go for a 3 by 3 filter. So we multiply each pixel element by 1, that means retaining its value, summing it over and dividing it by 9 to get the average. Remember that, also remember that we are doing either convolution operation or correlation operation in order to get our results. So we have learned convolution and correlation in the last lecture. So if you have not followed it or if you still have a confusion, please check the lecture video of that particular lecture. Now we have already discussed the similarity or differences between the two similarities, both of them 3 by 3. They are also called box kernels. Just that here this is more directional. This one treats all the elements in the same way. This one treats horizontal and the vertical lines in the image in slightly stronger way, saying that it gives higher weightages to them, while the elements at 45 degrees will have less weightages. So the averaging is get little skewed to highlight one region or to may not highlight the other one. And then we have seen the impact here. Primarily, we had seen the impact of increasing the size of the kernel. So larger the kernel, the more is the averaging. So smaller kernel, you will find that some sort of averaging has been achieved in these sections, but this is same, this is same, this is same. But as you increase the size of the kernel from 3 by 3 to 5 by 5 to 9 by 9 to 15 cross 15, you will find that the blurring increases. Here, even the larger objects are fairly blurred, but still readable. But here is an extreme example of 35 cross 35. Remember, this image is 100 cross 100. So when you say 35 by 35, actually your kernel size is one third. Your box kernel is this much. And you can see that if you have a this much size box kernel, this much size filter, then it is going to average most of this letter, large letter. So even the largest object in the image gets blurred with 35 by 35 filter. So that is what we have already learnt and understood. What are the uses? So this is one of the uses. Typically, this is the image of a section of the sky obtained using Hubble Space Telescope. Now you will find that if suppose I have to distinctly figure out how many galaxies are there, then all I need to do is there may be galaxies, these bigger ones, but these smaller ones, they might be stars. So I don't know what is what. So I can take this theory that the smaller ones are stars and larger ones are galaxies. So all I can do is, or maybe smaller ones could be noise. You never know. So all I can do is I can produce an averaging. Once I produce the averaging, you will find that a lot of these smaller details have vanished. So this has gone, these smaller details have almost vanished. And then I can use a suitable thresholding. You know what is thresholding? We have already discussed. So this becomes perfect white and this becomes perfect white, while below threshold objects becomes dark. So this becomes dark. You can see that all these background blurs, they all vanish. So the only distinctly looking part of the image is retained. And now you can see that you can very easily count these paths. You can always write a software which says that whenever it encounters a 1 that is bright, it will count as 1. Whenever it is dark background, it is 0. So it can always do this counting work. And you can count, you can find the density of galaxy, and if you have large such data, then this kind of automation is very helpful. For example, a typical Hubble's telescope or any Earth-based telescope can produce thousands of such images. Now, observing them manually and counting is very challenging. You can always introduce these kind of approximations and get your work automated. Important role is played by a blurring filter. So there are certain advantages. Advantages we have seen, these blurring filters are very quick to use. You can experiment with them. You like all 1 1 1 1, see the result. If you don't like, discard that and use the directional one 2 4 2. I have shown you two filters so far. There could be more also. So you can design your own filters, do a quick experimentations and get the results. And most of the time, the results are visually acceptable. So these are the advantages. There are disadvantages of these filters as well. So most of the time, you you would like to blur the image so to a to the up to the standards of a real physical lens blurring. Then this kind of filters will not give you very good approximations. Just to give you an example, now these days in mobile cameras, a very important feature has come which is called portrait mode. Now what does it do? Of course, it segregates the human face from the background. That is one thing it does. But apart from that, the other important thing it does is it uses algorithms to blur the background. Now, in order to blur the background, the impact of background blurring should be very much similar to a lens blurring. That is a preferred way of blurring. If you look at, if you have seen an image in which the background is blurred by a very shallow depth of field by using a wide aperture lens, you will find that the background blurring is very circular. If there is any light source in the background, then it gets expanded into a circle. Now, this kind of results, if you want, by the filters that we have seen, then it is not possible. The blurring introduced by the two filters that we have discussed so far or seen so far does not match with the characteristics of lens blurring, which is desirable. The reason is the lens blurring is always radially symmetric, while our filters were directional. So that is one of the drawbacks. Our filters introduce blurring only along the perpendicular directions. So one of the ways to introduce or to sort out this problem is using Gaussian kernels or Gaussian filters. This is a Gaussian functions which I have shown here over here. Now, one of my strongest suggestion to all of you would be this, that master Gaussian. Gaussian function was designed by Gauss, who was a master mathematician. Please read more about him. Mathematicians give him the level of respect that physicists give to Newton. Sometimes mathematicians argue that he was the greatest ever. So please read more about him, and please read more about his Gaussian function, which has been presented over here. What I am presenting over here is a two-dimensional Gaussian function. S and T are along the two dimensions, S1, T1. So you can take them as two axes. Say one axis is S axis and one axis is T axis. You can take K value as 1. You can take standard deviation sigma value as 1. And then you can see that this function is radially symmetric in two dimensions. The values are given over here. So when K and this is 1 and this is 1, and this you can always plot. In two dimension, it can look like this can be replaced by r square upon 2 sigma square, and it can of course extend it to a three dimension as well. You know that the Gaussian function gives to famous statistical bell curves, etc. So please read more about it. You have to be a master of Gaussian before you get into the next chapter. So right now you can do bare minimum for your forthcoming examination and then read more. So you can see that this is a radially symmetric function, and I can use these parameters to create a kernel for the image. This is a non-normalized. This is how the graph would look like. This is how the graph would look like. So if I take this as my function, you have seen r square is nothing but s square plus t square. So this is t axis, this is s axis. Then you can see that the function maximizes at the center, that is the origin, and then drops rapidly. You will find that if sigma value is say 3 and beyond, sigma represents how much is the deviation from the center, standard deviation. If the sigma value is 3 and beyond, then the value of the function g drops drastically. So practically using a g with larger sigma is ineffective because the coefficients drop. So once you normalize it, you can create your Gaussian filters, and you can use the Gaussian filters to get the kind of or a better results. So look at the results over here. I have a typical image over here. This image is has a background which is dark, and it has a bright patch over here. You can also call this image as, say, a image of a slit cylinder, say the kind of slit we use in our spectrometer experiments. So this is just a slit. What would be its intensity profile? So if I plot a graph of intensity about this axis, dotted line, then anywhere in this region, the intensity is zero. So the intensity is zero. And then from here to here, the intensity reaches to a maximum. There is a sharp jump in the intensity. Intensity reaches to a maximum. It remains maximum from here to here up till the width, and then finally the intensity drops at this edge. So intensity will drop, intensity becomes minimized, zero here. Now this is image which has been passed through, say, a spatial filter 111111111 box kernel, which we had seen in the last class and we revised in the beginning of today's class. So it introduces some sort of blurringness over here. Now, after the blurring has been introduced, we can check the intensity profile along this axis. The intensity profile along this, you can see, is intensity is 0 up till here. Then you can see, interestingly, the intensity increases linearly. So intensity increases very linearly from here to here, again become constant, and then again drops linearly. So intensity drops linearly, again becomes zero on the other end. But this is the result of a Gaussian filter, as we have discussed in the previous slide. If you apply the Gaussian filter and transform the input, you would find that the output has a more subtle variation. It is no longer a ramp, no longer a straight line. It has a curvature over here, it has a curvature over here. It actually resembles here one of the standard bell curves or the Gaussians. So this is how the impact comes. This kind of impact is going to come in all the part of the images. One important issue that we did not discuss earlier and now we can is what happens when you do a padding or when you don't do a padding. So here I have three images. If you don't do a padding, typically we have learned in the last class that we need to do padding. If you don't do the padding, then the last part becomes fairly uh, imbalanced. Border effects come in. Any matrix placed at the border, the outside elements, if you don't do padding, then they have nothing to multiply. By default, it takes the value 0 and reduce the pixel values at the border. So you will get a border there. And typically when you use a padding, say, then padding depends on what padding you use, depends on your image. You can always pad it with 0. Sometimes people pad it with 1. Once you do that, you typically get a border over here, which is not a dark border, but somewhat matching to this center, but uniform border. While this is here, the third case is the mirror padding, where the padded elements are the mirror image of the elements which are inside. So suppose if I have a 0 here, then I will pad it 0. But if I have a 1 here, I will pad it with 1. So in that case, my output here, the border is more similar to the image element. So if it's a dark region, border will be a bit darker. while here the border will be a flat gray. So that difference comes in. So when you will do your processing in Python, you will see these effects as well. Now I'm going to talk about some non-linear filters, but very briefly. We are going to talk about them in detail in the next chapter. So they also operate on neighborhoods. They also operate on, say, some region 3 by 3, 5 by 5, 7 by 7. But their operation does not involve any calculation of other thing. They just operate on one of the pixel values. So I'm going to show you one of the example is the median filter. So what it does is that it takes a particular neighborhood, take all those pixels together, and it calculate the median, finds the median of all the pixels, and then replace the central pixel in the resulting image by the median of the selected region. So you can use the median. Then there is a max filter. Now max filter is typically selects the most bright point in the given region. Suppose if it's a 3 by 3 max filter, listen to me carefully. So if it is 3 by 3 max filter, then there will be 9 elements. The filter checks in those 9 elements which image pixel has the highest intensity. The one which has the highest intensity is retained in the final image and rest are discarded. So this way it keeps selecting the brightest point in the given image. Similarly, a minimum filter, it is used to find the dimmest point or the least intense point in the given region, 3 by 3, 5 by 5, whatever regions you choose. So they have their uses depending on what kind of situation arise. Here I have an image over here, left side. It has been corrupted by a salt and pepper noise. So if you can see this carefully, it is called salt and pepper noise. Now what is salt and pepper noise? I mean, people use salt and pepper for making food. They keep it on their tables so that they can add to their food while eating. Now what is salt and pepper doing here? So salt is white. So if an image is corrupted by white points, lot of white dots, then it is called salt noise. While if the image is corrupted with the dark points, then it is called pepper noise. So now in this case, now when you say dark, pepper noise is dark, which is typically 0 or very low value, while salt noise is white, which has a very high value. Now if you use a 3 by 3 averaging mask, averaging mask just averages the bright and dark and does not remove them either. But if you use a median filter, then what median filter is taking each neighborhood, selects the median value and may use that to create the new image. So new image at every point is the median of the neighborhood. So you take a small neighborhood here, find out the median, replace this pixel by that median, and so on and so forth. So once you do that, since the median by definition is the middle value, it will discard both the very bright as well as very dark values, and therefore both the noise, salt and pepper are removed over here very smoothly. So this is an example of use of a non-linear filter. Other example of a non-linear filter is in this image. You can see that this image has large amount of noise, especially if you are watching on a laptop. Perhaps you should be able to see there are so many dots over here, 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 here. And if you use a noise removal order statistics filter, then what you get is this. You can see that most of those noise elements are gone. If you want, I can show you again. Look at this and then look at this. Maybe once again, this is original. See that lot of noise. You can see that the noise has gone. So there are many these kind of filters which we are going to use, maybe some more in the next chapter. Now that brings us to what is called sharpening filters, or in other words, high pass filter. A sharpening filter is nothing but it sharpens the edges, the the points which are often repeated, small details, while it makes you lose the large objects. Small parts, small details are enhanced, the large size objects are neglected. So that is called sharpening or high pass filter. Typically, we use the process of derivative to achieve this effect. How do we take the derivative? In discrete manner, derivative of a function, in this case it's an image function, is defined as, now this is the fundamental definition or the definition of derivative. If you remember, f of x plus h minus f of x upon h. H is 1 here, so f of x plus 1 minus f of x divided by 1. Since we divided by 1, we don't write it, so it's just the difference between the values of two adjoining pixels. So derivative of a pixel is nothing but the difference between the values of the two adjoining pixels. These are the values f. So some of the important thing, it must be 0 in the area of constant intensity. It is obvious. If two points have the same intensity, then their values will be same. Therefore, the first derivative, if you take a difference, it must vanish. Must be 0. Must be non-zero at the onset of an intensity step or ramp. So if the intensity increases from any pixel onward, suppose you are a pixel A, on pixel B the intensity increases, then obviously the intensity change has to be non-zero. So the first derivative will become non-zero. It also be non-zero along the intensity ramp. Now what is an intensity ramp? An intensity ramp is something where the intensity changes continuously. So if that happens, then it should be non-zero. So typically the first derivative gives you the slope of the intensity. If you observe it carefully, constant intensity, it is 0, but when the intensity is changing, it is non-zero. So that means wherever the intensity will change, the first derivative will exist. Wherever intensity remains constant, first derivative will vanish. So first derivative typically will not give you the edges. What does it give you? It gives you gradients. What is gradient? You know, gradient is something when something changes with position. What is changing with position over here? Intensity is changing with position. So if the intensity is changing with position, then the intensity gradient exists. The first derivative will give you that intensity gradient. Larger the intensity gradient, more would be the value of the derivative. And so in the region in which the intensity gradient is large, you will find that your image has become your gradient image has become brighter. In the regions in which the intensity gradients are small, you will find that intensity or the first derivative image has become darker. Remember, it does not give you the edges only. It gives you the change in the change in the intensity values. Now, what do we do in order to get the edges or sharpening? So, in order to get the edges, we need to take the second derivative. So, what you do is you take the first derivative and you apply the second derivative. So, when you do that, and you can do this and check in your rough, it will be given by f of x plus 1 plus f of x minus 1 minus 2 of f of x. So your central pixel has to be doubled and it has to be subtracted from the sum of two neighboring pixels. Remember, I'm talking only about x-axis. So you take your central pixel is f of x. You take the two neighboring pixels to the central pixel, add them, they will give you a large value, minus subtract 2 of the central pixel or twice of the central pixel, and that should give you the second order derivative. So remember, it has to be 0 in the area of constant intensity. Why should it be 0 in the area of constant intensity? Answer is simple. If the first derivative or the first order derivative does not exist in a given area, obviously even the second order derivative will not exist. Must be non-zero at the onset and at the end of an intensity step or ramp. So whenever there is a change in the intensity step, intensity step means intensity increases, intensity ramp means intensity decreases. Whenever there is a change in the intensity, it has to be non-zero, but it is zero along the ramps. If the intensity is changing continuously, then the second order derivative will also vanish because the first order derivative becomes constant on the ramps, and therefore on the ramps, on the constant intensity changes, the second derivative will not give you any value. It will not give you any value if the intensity does not change, that is constant. It will give you the value only when there's a change in the intensity, and that is how we say that it retains only the borders, only the edges. What is an edge in an image? It is a change in the intensity that is reflected. So if you get more, here is my one sample drawing. This is my one-dimensional image with the gray level values. It's given 666654321011111666666. Here is the one-dimensional plot, intensity versus position. So all those 6 are plotted over here. So from here to here it is 6, constant intensity, so straight horizontal line. Then 4, 5, 3, 2, 1. So there is a drop in the intensity, a ramp. This is a intensity transition point. Intensity starts dropping. Again intensity becomes constant, all 1 1 1 1 1 here, and then there is a step. Intensity starts increasing. In fact, it increases very rapidly. Just in one step it increases from 1 to 6, and then again it remains constant. Now what would be the first derivative? The first derivative is this minus this minus this minus this minus this, so on and so forth. So here are my first derivative values: 0 0 minus 1 minus 1 minus 1 0 0 0 5 0 0 0 0. What would be my second derivative? Obviously second derivative is derivative of the first derivative. So the earlier page definition I had given you from the derivative of f of x, but I can take the one more derivative of the first derivative to get the second derivative. So this minus this 0, this minus this, this minus this, minus 1, this minus this 0, this minus this 0. So you can see that wherever the first derivative was constant, the second derivative vanishes. But whenever the first derivative changes, or wherever there is a jump in the intensity here or here, the second derivative survives. So at this change in the intensity, the second derivative survives. Here the intensity is constant, the second derivative vanishes. Here the intensity changes, 0 minus 1 or 1 minus 0 will give you 1. So the second derivative survives. Then here the intensity is constant. The first derivative vanishes, second derivative vanishes. Here there is a sharp rise in the first derivative, and the second derivative also there is a sharp fluctuation, plus 5 here, minus 5 here. So why these two? Because there is a sharp change from here to here. There is one intensity change. You go from a constant intensity to an intensity shoot. So that will reflect plus 5. You have a sharp upgoing edge, and then from a sharp upgoing edge you get into a flat intensity region. So that reflects another change in the intensity. So this is one edge, this is other edge. The other edge is reflected by minus 5. So 0 minus 5 is minus 5. So that's why you get 2 points over here. One is reflecting this edge, other one is reflecting this edge. You can see that they have different values, plus 5 and minus 5. So if you look at the second order image, this will look bright and this will look dark. We will come to that with an example very soon. Rest is 0 because it is constant. How would the second derivative plot look like? The second derivative plot looks like the first derivative is dot, second derivative is box, the second derivative is 0, it shows a bump here, then again remains 0, shows a bump here, shows a positive bump, shows a negative bump, shows 0. Okay, so going ahead, these are the two pictures kept in the same plane, same slide, so that you can compare. So you can see that it shows a jump regarding this, shows a jump regarding this for this one and for this one. Now in a real image you will be doing sharpening second order derivative in 2 dimensions, that is dimension x dimension and dimension y. So we typically use Laplacian for 2 dimension, you are familiar with. So these are individual dimensions I am writing here. I suggest you to work out these two in 2 dimension. It will appear to be this way: x plus 1, x minus 1, y plus 1, y minus 1, minus 4 times the central pixel, 4 times f of xy. So I would strongly recommend that use these two and work out for these two. So how would the kernel look like? So you can see that one of the ways the kernel can look like is this is coefficient is 1, this coefficient is 1, this coefficient is 1, this coefficient is 1, this coefficient is minus 4. This is the central. So this is how the kernel can look like: 1, 1, 1, 1, minus 4. The rest of it are 0. So this is the way it can look like. This is, if you want to improve it in some ways, you can do that. So you can increase the extent of derivative if you make it minus 8. You can revert it, you can make this as plus and these as minus. So minus 1, minus 1, minus 1, minus 1. This is plus, or all these are minus and this is plus. So you can see, always remember that the 1, 1, 1, 1, 4, if you add all these coefficients, they will lead to 4. This is minus 4, total is 0 in a sharpening filter. Here also, if you add all these ones, it is 8. This is minus 8, total is again 0. Why the total should be 0? Please find it out. I'm leaving for you people to figure it out. Here is one example of this Laplacian kernel. This is a little bit of smoothened, blurred image of the moon, which you can try clicking by a camera. Somebody had clicked it in the Diwali break. So you can use that image to apply that Laplacian kernel. And this is the, you can see the edges. So you can see that the boundary is sharp, and you can see that this boundary appears over here. Then you will find that all these edges, you can see that, for example, if you take this big crater here, or whatever you call it, lake, crater, whatever. If you see that, then here this part is white, this part is dark. But if you look at corresponding here, then inside is also dark because this is constant intensity. So it is dark. The outside also is constant intensity, bright. So even that is dark. Okay. Now look at the transition. The transition has a bright line which actually represents the transition from the constant intensity on this side to the dark side. So that line is retained. The edge is retained, remember. So edges are retained. Here also the edges are retained. So this is an example of Laplacian kernel applied, or second order derivative applied to extract the edges. This is extracting the edge from the image. Remember, we are still not making the image sharpening. Now in the next class, we are going to discuss how to sharpen the image, and we are also going to look more into the difference between the gradient filter and edge detection. These two processes are very close and students suffer confusion. So I would like to clarify these two issues in the next class. We can stop here. Thank you.